So let's look at some applications of the semi-classical approximation. So what we have there is we've got the nonlinear Schrodinger equation that we get from a particular Hamiltonian for a particular system, and we've seen how to derive it if we have a more complicated system with more internal states or more spatial degrees of freedom. Now the semi-classical equation can't be right all the time, but it turns out to be surprisingly useful. We can always find quantum effects, and indeed that's why we have a quantum field theory, because we have discovered that this theory is actually correct. But we did very well for a long time with the semi-classical theory of photons, also known as classical electromagnetism. And this semi-classical theory for a massive field also works surprisingly well for certain physical situations. One of the main surprises about Bose-Einstein condensation was how effective these semi-classical theories could be. And indeed, if you have only linear processes, for example, evolution in some external potential, even if that potential is time dependent, coupling between different internal states of your atoms, even weak BEC excitations, manipulating them with optical or magnetic potentials, atom lasers, vortices, solitons, waveguiding, feedback, all those things can be described surprisingly well just by your semi-classical equation of motion. So as an example, let's try and find the ground state of a bunch of particles in a trap. So in the semi-classical approximation, we're always going to be evolving under this equation, which means we're never going to have zero time evolution, but just like we have for the Schrodinger equation, we'll have a steady state when that time evolution is simply a rotation in phase, which means that this part here has to be just proportional to the wave function itself. And because we're not dealing with a single particle, we call that energy not the total energy, but the energy required to add one more particle, which is also known as the chemical potential. Now, of course, when that nonlinear term there is zero, then that is exactly the normal Schrodinger equation, energy eigenstate equation. And so, of course, we get the normal energy eigenstates in that case, which is entirely unsurprising because if we have a large number of atoms that are completely not interacting, then the ground state of the entire system is when all the particles are in that ground state, and we know exactly what that ground state is. But obviously when that term is non-zero, then if it's positive, then we're going to see the atoms repelling each other, and so that ground state is going to have to be a little bit bigger, a little bit spatially wider. And if that U is negative, then they're going to be attractive, and so we're going to see that wave function get a little bit narrower. Now because this equation is nonlinear, because of this term here, it's quite difficult to get an analytic form for that solution, except in various limits. The limit when that nonlinear term is zero, of course, is trivial. We go back to the linear equation and we have tools for that. The other regime where it's actually easy to do is when that U is extremely large. When that U is extremely large, then in fact you can ignore a different term. You can ignore the kinetic energy term. This is known as the Thomas-Fermi approximation. When does this apply? It applies when the nonlinear energy scale is much larger than the natural energy scale for the linear problem. Note that the nonlinear energy scale depends not just on this prefactor U, but also on the coherent state approximation, the order parameter. And the order parameter is not normalized like a single particle wave function. The more particles you have, the larger that is. And so it depends on how many particles you have, whether or not the interactions are strong. So if you try and put a large number of particles into a box, that acts like strong interactions, just the same as if you put a few particles that very strongly interact into that box. And if you put sufficient number of particles into the box, then your final shape is determined far more by the shape and size of that box and the interactions than it is by the kinetic energy, which is what used to keep the particles from all going into the very, very bottom of that potential. So in that situation, the equation is enormously simpler. In fact, it's algebraic. It's not even a partial differential equation anymore, and so we can solve it right here, at least up to a phase. And you'll note that the solution just looks like an upside down potential. So it's as though we have some potential and we were to pour our wave function in like liquid chocolate, wait till it sets, turn it upside down, and there you have your wave function. The nonlinear Schrodinger equation is not just useful for static effects, you can also look at dynamic things. A good example of that is vortices. So if you take a rigid body and you try and spin it around some axis, then of course you can spin it at any speed, and at a particular point on that rigid body it will be traveling at a velocity, and you can get that velocity from just the rotation and the distance from that axis. And that can be arbitrary. But when you have a fluid, when you have a quantum fluid, then in fact we're not describing single point particles here, we're describing an entire wave function. Now if you take a wave function, the equivalent of velocity is a gradient in the phase. So if I have a quantum fluid that's actually defined by a wave function, and I try to spin it around some axis, then by trying to have a constant velocity going around a circle, what I find is that I need a constant phase increase going around this circle. If I have a phase increasing and increasing going around the circle, of course, I can't do that arbitrarily because I'm going to have some kind of discontinuity when I come back. So I have to have the phase well defined at a point, which means the only way I can do this is if we have quantized rotation. And this quantized rotation is called a vortex. So in simple terms, if you take any wave function and you trace a loop in it, then you have to come back to the same phase. And that same phase is only defined up to a multiple of 2 pi. And so if you integrate your phase along that loop, you have to get some multiple of 2 pi. Often 0. If you have something that isn't 2 pi, if you've got 6 pi or minus 10 pi, then you have what's called a vortex. And the charge of the vortex is how many multiples of 2 pi that you have. What this means is if you put a stirrer into, say, a Bose-Einstein condensate, and you slowly try and stir it up. So you might be trying to excite some kind of rotation. If you do that too slow, you're actually going to get no effect whatsoever. The wave function will simply stay with no rotation in it. And that tendency to resist excitations or damping is a classic feature of superfluidity. If you go above that critical frequency, then you'll end up getting some rotation. And that rotation will form a vortex. If you have a vortex with a charge of 2 pi, also known as a winding number of 1, then that's obviously stable. If you have one with 4 pi, or a winding number of 2, it's not obvious whether you're going to have one big one, or ultimately have it break up into 2 smaller vortices, each with a winding number of 1. So the total winding number is conserved, but it doesn't necessarily have to stay as one highly charged vortex. It can break up into small ones. It actually turns out that energetically it's favorable to form a lattice of small vortices, and that's what happens when you try and stir these things up. And here we have some beautiful examples of that taken from ENS in Paris and MIT, respectively. In both of these pictures you see the results of stirring the condensate harder and letting it relax to its equilibrium position, and you can see that the number of vortex cores in it go larger. Of course, you can't have a well-defined phase at the center of the vortex because it has to have all the phases going all the way from 0 up to 2 pi at once. And in order to resolve that, what it does is it has zero density there, so the field has to be 0 there, which is why you have those cores that you can see right through. So these are just a picture looking straight through a slice of the condensate, which they illuminate using fluorescence, and you can see that you get all these different vortex cores, and all of those happen to have a charge of 1. And they're more or less in the equilibrium position, which makes that lovely triangular lattice. So these are the things you can kind of do with the semi-classical approximation where you're describing a single component field of a massive particle, for example a bunch of atoms with no internal state structure that matters. There are plenty of physically important cases where the internal structure of the atoms that you're trapping do matter. One classic example would be the atom laser. An atom laser is where you try and make a coherent beam of atoms, and you make a coherent beam of atoms in analogy with the way you make a coherent beam of light. You take a large number of atoms, all in the same quantum mechanical state, in other words, a Bose-Einstein condensate, and you couple them to the outside world where they form a beam. In the same way, in a laser, in an optical laser, you take a large number of photons all in the same mode in a cavity, and you couple them out through a partially sealed mirror so that they come out into the outside world. Now suppose our atoms are all in the f=2 spin state. That still gives them 5 possible projections of their spin onto any given axis. So a magnetic dipole in a magnetic field has an energy that's proportional to the projection of its dipole along the magnetic field. If we organize to have a magnetic field whose magnitude has a minimum at a particular point, then we're going to see a trapping potential for the particles in a particular spin state. Now the particles with MF=0 are not going to see that trapping potential at all. They're not going to see the magnetic field. So they'll just typically have gravity. So if we have this in the direction of gravity, those particles will just see a potential that's a straight line. And of course, the particles with MF=1 will have a trapping potential, but 1/2 the strength of the MF=2 ones. And similarly, the other two MF projections will be anti-trapped. They'll actually be repelled out of this area. And I've tried to fairly accurately draw there the fact that these trapping potentials are going to have offset centers. The peak of the anti-trapping there, and the peak of the anti-trapping there, and the trapping bottom there, and the trapping bottom there should all be differently spaced because of the gravity that's on top of everything. So you've got the trapping or anti-trapping potential plus gravity in all these cases. So if we maintain the magnetic field at a non-zero value, then the atoms will tend to stay in their particular MF projection. And so if we start them in the trap state, they'll stay in the trap. If we start them in the anti-trap state, they'll fly away. While they're still in the magnetic field, they'll still stay in that MF state. If we want to deliberately couple some out, then we're going to need to change the MF state, and the easiest way to do that is to apply a radio frequency transition. And the radio frequency transitions, if they're resonant with these energy differences, they should cause a transition at that point. Now, I haven't drawn that particularly regularly, of course. There should be a lot more structure to that. How would we model that? How would we model having all those different radio frequency transitions? Well, the simplest way is with the nonlinear Schrodinger equation. We follow the same process we followed before, and you end up with something like this. So because in the Hilbert space for our single particle, we now have an index for the MF component as well as the position. That means that our field operators have both indices, and that also means that our order parameter has to have both indices. And so if we have 5 MF levels, we have 5 component wave functions for our order parameter. And this row here is shorthand for the sum of all the densities. And it's like that because we're assuming that the interactions between all the different MF states are identical. They don't have to be, but for this model we can make that assumption. And this is just 5 lines of the GPE that we derived earlier, except we've got coupling between the different fields. You can see we've got coupling between different MF states there in that big matrix. And we have identical interactions between each component. That's just a partial differential equation. We can easily put that on a grid and solve it. And we'll do that together later, and we'll discover that this system has some quite interesting behavior.